say? Question number 1. It says, if a charged particle moves in a straight line through some region of space, can you say that the magnetic field in that region is 0? Yeah, you can say anything you want, but you can say that the magnetic field in that region is 0 if that's what you want to say. But that's not the only answer that you can come up with. What else can you say? Well, if there's a magnetic field within that region, obviously, if the charge is moving parallel to it, it's not going to experience any force. So that's one of the things that you could say. If a charge is moving parallel to the magnetic field, nothing is going to happen. All right, but if the charge is moving across the magnetic field, obviously it's going to get deflected. All right, so which means that you cannot conclusively say that the magnetic field is 0, especially if the charge is moving parallel to the magnetic field. So that was the answer that I was looking for question number 1. Question number 2, how can the motion of a moving charged particle be used to distinguish between a magnetic field and an electric field? Give an example to justify your argument. All right, so one of the things that most of you guys end up missing is, all right, so question number 1 is this. Question number 2, if there's an electric field acting on a charged particle, I was looking for a straightforward answer, nothing poetic, just get to the point and stay with it type of thing. If an electric field acting on a particle, it's going to cause the particle to accelerate along the direction of the electric field. So I was hoping that you guys would keep it simple. The charged particle will accelerate along the direction of the electric field, meaning that if it's a positive charge, it's going to move in the direction of the electric field. If it's a negative charge, it's going to move in the opposite direction of the electric field. Charged particles in the presence of the magnetic field, what's going to happen to the charged particle as it's going across the magnetic field? It's going to experience a force. It's going to be perpendicular to its motion, so which means that it's going to go into a circular motion. All right, so most of you guys said, oh, it's going to move in a circular motion, but once again, there's acceleration involved, right? All right, if there's a force acting on something, it's going to accelerate. So there's a magnetic force causing this charged particle to accelerate. So in both cases, they will experience acceleration. This one is going to accelerate along the direction of the force, and this one is also going to accelerate, and the acceleration is going to happen perpendicular to the direction of the motion. That's it. So it's going to go into a circular motion. So question number 3. Justify the statement, it's impossible for a constant magnetic field to alter the speed of a charged particle. Most of you guys kind of missed that point. I mean, you guys made statements, and they were actually more or less correct. It's not that you're incorrect. The explanations are usually insufficient. Something is missing. In the presence of a magnetic field, the charged particle is going to go into circular motion. And obviously, so this is what happens. Boom, boom, boom. It's going to go into circular motion. Let's check to see. All right. So the motion is going to be in this direction. Let's pretend, and there's a magnetic force acting on it. For the speed to change, the work has to be done on this charge, which means that the energy needs to be transferred to this charge. All right, so work by definition is force causing displacement. Force and displacement need to be in the same direction. Force and motion need to be in the same direction. What that means is the force has to have a component along the direction of motion. Guys, the force is in this direction. The motion is 90 degrees to it. So no work is being done. Because no work is being done, then no kinetic energy is being transferred. All right, so which means that this thing cannot speed up or slow down. I think a couple of you guys got this 100% correct. And most of you guys kind of missed the point on this one. All right, moving on to the next question. So how can a current loop be used to determine the presence of a magnetic field in a given region of space? Well, once again, some of you guys nailed it. Some of you guys came pretty close to this one. When you have a current loop in the presence of a magnetic field in a given space. All right, so let's just pretend that you have this current loop. So the current is going to be going around. And notice that that's got some kind of a cross-sectional area. So what that means is this is going to act like a magnetic dipole, moment. So if there's an external magnetic field within that region, this magnetic dipole moment is going to try to line itself up in the direction of the external magnetic field. So what's going to happen is it's going to experience a torque. It's going to experience the torque moment. That's it. While trying to align itself in the direction of the external magnetic field. All right, so that's the answer I was looking for. So question number 5. All right, question number 5 is about a bubble chamber. It says, it's a device used for observing traces of particles that pass through the chamber, which is immersed in a magnetic field. If some of the tracks are spirals and the others are straight lines, what can you say about these particles? What can you say about the particles? All right. So it's a bubble chamber within which some of the particles are spiraling. So that's straightforward. Bubble chamber means that you got these magnetic field lines are either within that region pointing into or out of the page. All right, so this is what we got. So what happens when you have charged particles coming in? When you have charged particles that you send in, imagine that this is a positive charge particle, you just send it in, it's just gonna go in a spiral motion. So that's what happens to positive charges, let's assume. All right, evidently let me see, okay, this direction is fine. And then if you send in negative charges, they will spiral in the opposite direction. All right, so these charges will spiral in the opposite direction. So spiral motion is gonna happen to positive and negative charges. All right, because moving across the magnetic field, they will experience a force that's going to be 90 degrees to their motion. So they will spiral around within that region, depending upon their speeds. And uncharged particles will go right through them. All right, so you got an uncharged particle. This is the one that's just going to go right through. Right, and that's it. So those are the answers I was looking for.